Hello everyone, we are Graphicscape, and we're here to present our final year project, the Brand Visuals Registration and Lookup System. We'll start with the project's background, the problem we're solving, and our key objectives. While websites use text-based domain names, brand identity is visual. We recognized a disconnect. There's no standardized system for registering these crucial brand visuals, like the logos you see here. Our project aims to bridge that gap. This brings us to the core problem. First, domain registrations are text-only. Second, a DNS-like system for visuals would be invaluable for protecting brand identity. And finally, most image retrieval systems focus on raster graphics, leaving the more appropriate vector format, which is used for most logos, as a less explored area. This is the gap we aim to fill. Our primary goal is to create a complete brand visual system that works end-to-end with vector graphics. To do this, we have two objectives. First, to identify the best methods for a registration system, allowing companies to register their logos. And second, to develop a lookup system that can accurately find a logo even if the search image is partial or altered. To clarify, our work focuses on vector graphics, or SVGs. Unlike pixel-based images, they're defined by math, making them infinitely scalable without quality loss, easily editable, and very efficient. However, working with vectors is challenging. Most comparison tools are built for pixels, not shapes. Research has focused more on generating vector images, not comparing them. And crucially, two logos can look identical, but have completely different underlying code, making simple comparisons impossible. Our system had to overcome these hurdles. Now, let's look at our methodology. Our system has two main parts: a registration system, to register logos and prevent duplicates, and a lookup system, for public searching. This diagram shows our research process. We tested both algorithmic and deep learning methods on a dataset with real-world distortions. We then used the mean average precision metric, or MAP, to evaluate the results and select the best approach for our final system. Here is the workflow of our final system. An SVG image is submitted, pre-processed, and then analyzed by two parallel pipelines, a deep learning comparison and an algorithmic comparison. Each pipeline finds its top match. If they agree, we get a final similarity score. If not, a color-based comparison acts as a tiebreaker. This final score determines if the image is a duplicate or can be approved for registration. The innovation lies right here, in this parallel processing step. By using both a deep learning approach for semantic understanding and an algorithmic approach for precise geometric matching, we leverage the unique strengths of each. This is our system's technical architecture. When an SVG is processed, its path data is sent down two tracks. On the top track, our deep SVG model encodes the image into a compact numerical representation, a latent vector, and compares it to our database using cosine similarity. On the bottom track, Procrustes analysis directly compares the geometric point clouds of the shapes. Fusing these two distinct analyses gives us a far more reliable similarity assessment. Procrustes analysis is a powerful statistical method for comparing shapes. We convert each shape into 250 outline points. First, we center the shapes by moving their centroids to the origin. Next, we scale them so size doesn't affect the comparison. Then, we rotate and reflect one shape to best match the other. The final score measures how much they differ after being perfectly aligned, giving us a clean measure of shape similarity. For our deep learning path, we chose the Deep SVG model. Deep SVG is a hierarchical transformer-based model for learning and generating vector graphics. It consists of an encoder and a decoder. The encoder first processes each shape, then captures their relationships. The decoder predicts shapes and attributes and then generates the final SVG drawing instructions. In our method, we used a four-step process. First, we pre-process the SVG data. Second, a transformer-based encoder creates a latent vector, a rich numerical summary of the logo. Third, these vectors are stored in a high-speed Milvus database. And finally, we use cosine similarity to find the closest matches with incredible speed and accuracy. If our main pipelines disagree, we use color comparison as a tiebreaker, providing an additional layer of verification when shape alone isn't enough. Color comparison in SVGs is tricky. Our method extracts all hex color codes, converts them to the LAB color space, which mimics human perception, and uses a standard formula to measure the visual difference. The final score reflects the proportion of matched colors, giving us a human-aligned measure of color similarity. The final step is score normalization, which is crucial for fairly combining the different scores from our two pipelines. To combine the scores, we use z-score normalization to put them on the same scale. Then, we apply quality weighting, giving more influence to the more consistent method. The final fused score is a weighted average of the two. This fusion process creates a single, reliable similarity score that represents the best judgment of both our pipelines. We also convert pixel images like PNGs into high-quality SVGs, which are then fed directly into our main analysis pipeline. Next, let's review our experimentation and results. As a reminder, our process involved testing multiple methods against distorted images to find the most robust solution. We tested 4 algorithmic methods: Procrustes, Hausdorff, Earth Movers Distance, and CDAF, each with different strengths in geometric comparison. On the deep learning side, after exploring several models, we chose DeepSVG for its powerful transformer encoder and suitability for retrieval tasks. We also fine-tuned the DeepSVG model on a large dataset of logos. As this table shows, this led to modest but consistent improvements in accuracy, especially for handling real-world distortions like occlusion and contour changes. For a fair comparison, we created a benchmark dataset. We selected 5 widely recognized logos and applied 29 different controlled distortions to each, covering rotation, stretching, occlusion, and more. This gave us a query set of 150 distorted SVGs to rigorously test each method's performance. This chart and table show a detailed breakdown of performance. You can see clear strengths and weaknesses. For instance, most methods handle rotation perfectly, but in the occlusion category, DeepSVG clearly outperforms the others. This detailed analysis helped us understand the specific capabilities of each approach. Here are the overall mean average position scores. Procrustes analysis was the top-performing algorithm at 0.676, with the DeepSVG model a very close second at 0.634. This highlights a key finding. A well-implemented traditional algorithm can be just as effective as a deep learning model for this task. When we fused our top methods, the results were remarkable. Our final hybrid system achieved an overall MAP score of 0.794. As you can see, this is significantly higher than the best individual methods. This demonstrates the powerful synergistic effect of our hybrid architecture, proving it is greater than the sum of its parts. For a final practical evaluation, we registered 134 logos and tested the lookup with 100 query images. We achieved a precision of 85%. This real-world test confirms that our system is not just theoretically sound, but also practically effective and accurate for its intended purpose. Now, we'll give a brief demonstration of the system.
First, go to the Register Logo tab to access the submission form. Fill in your company name, website URL, description, and upload the logo. Click Check Similarity to ensure no similar logo exists in the database. If clear, click Submit to register. To look up a logo, go to Look Up Logo tab and upload a reference image. The system returns the top 5 results, with the correct match ranked first.
We now turn to the conclusion of our study. In short, our research confirmed that for vector graphics, both algorithmic and deep learning methods are powerful. We found that Procrustes analysis and DeepSVG were the top performers. This demonstrates that deep learning isn't always superior. By understanding the strengths of both, we developed a hybrid model that is more accurate and robust. In conclusion, while our system has some limitations, its applications are significant from duplicate logo detection to brand analysis. For future work, we plan to integrate OCR for text-heavy logos, improve matching under occlusion, and eventually support multimodal queries combining both image and text. Thank you for watching.